Every 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a non-profit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hi to everyone, my name is Daniele Antonioli and welcome to my seminar titled On the Insecurity of Vehicles Against Protocol-Level Bluetooth Threats. I would like to thank the Automotive Security Research Group for giving me the opportunity to give this seminar to all of you. Quick introduction about myself. I'm an assistant professor at Eurecom, a research center and university located in Sophia Antipolis in the southern part of France. I'm doing research in system security in the fields of mobile, wireless, embedded, and cyber physical systems. If you want to get more information about myself and my research work, you can visit my website. So, in this seminar, I will present the first study of protocol-level Bluetooth threats for vehicles. And I will explain why this is an explored but very relevant attack surface for the automotive. Then I will show you a methodology to assess these threats, including experiments in the lab and on the road. I will also show you an evaluation of protocol-level Bluetooth threats, where we evaluated recent cars against these threats with attacks such as spoofing a trusted smartphone to a car infotainment unit using 2 critical Bluetooth vulnerabilities that we disclosed in the past, KNOB, BIAS, and KNOB. I will conclude my talk by describing our low-cost setup that you can also reproduce in your lab to test several protocol-level Bluetooth threats, including BIAS and KNOB. Let's start by defining what is a protocol-level Bluetooth threat, or PLBT in short. So, before doing that, let's quickly introduce the field of automotive Bluetooth and automotive Bluetooth security. So, as we know, modern vehicles support wireless technologies, including Bluetooth, Wi-Fi, and cellular. So, in this talk, we are focusing on Bluetooth, that is a pervasive, low-power, and low-cost wireless technology that is quite popular in the automotive industry. A recent survey says that 2/3 of all cars in the market by 2024 will be embedded with Bluetooth. And Bluetooth enables several wireless services to enhance the driver user experience. For example, there are keyless entry systems that are based on Bluetooth that are capable of computing the proximity of the driver to his or her car and unlock the car automatically, only exchanging wireless packets. Another very common use case for Bluetooth is in-vehicle infotainment. And this is the focus of this webinar. In-vehicle infotainment is provided by a dedicated unit that we can see here in the picture on the right. This unit is a box mounted on the front row of a vehicle next to the steering wheel and is commonly known as in-vehicle infotainment unit, and we will refer to it as IVI during the talk. And the IVI has a display, several buttons, and it can be connected securely with a smartphone or with any other mobile device. And then once the two devices are connected via Bluetooth, then they can start exchanging packets, and they can provide several services. In this table, we are providing the most common Bluetooth services that an IVI is capable of providing when it is connected to a smartphone. For example, we have the Advanced Audio Distribution Service that in Bluetooth technical terminology is also known as a Bluetooth profile. And using this service, we can stream music from the smartphone to the IVI. Similarly, with other Bluetooth services or profiles, we can control the music or video player in the car remotely. We can manage calls. We can store and read SMS from the IVI. We can send or receive arbitrary data, arbitrary files. We can join an internet connection that is shared by a smartphone. We can store and read contacts. We can emulate a serial port and even access a SIM card via the IVI. So from this table, we realize that it's evident that IVIs are enhancing the driving user experience, but on the flip side, they are also interacting with sensitive data. And so it's very important that the Bluetooth connection between the smartphone and the IVI is secure. As any wireless technology, Bluetooth exposes vehicles to remote wireless attacks. These attacks are very important because they achieve safety and security issues affecting the driver and the vehicles by only requiring an attacker in wireless range sending wireless packets over the air. In this case, we are focusing on Bluetooth wireless packets, and these attacks are not requiring physical access to the vehicle. And broadly speaking, we can classify Bluetooth attacks on automotive into categories. The first category includes implementation level Bluetooth threats, and these are threats or attacks that are exploiting implementation bug in the IVI software. The IVI is a complex system. It includes several subsystems. One of these subsystems is the Bluetooth subsystem that is running some software that is the Bluetooth firmware. And if the Bluetooth firmware contains implementation level vulnerabilities, such as buffer overflows, integer overflows, and user after free, then an attacker can try to send a malicious packet that is triggering this implementation level vulnerability and achieve, for example, remote code execution. A recent example of implementation level Bluetooth threats on automotive is the Salinas IVI RAT, or remote access Trojan. In this work, the researchers demonstrated how to mount a remote access Trojan in an IVI by exploiting a combination of D-bus, Bluetooth, and SMS. This is a mature research area, and unfortunately, these type of threats are still present for several reasons. For example, the firmware that is compiled for the IVI typically is written in memory unsafe programming languages such as C, and doing so we increase the probability of having implementation bugs in the code. Another reason is that most of the times IVI firmwares are difficult to patch or even impossible to patch unless there is a recall of the vehicle. But this is not the focus of this talk. The focus of this talk is about protocol level Bluetooth threats. This is a known class of threats in the IT world, but is quite unknown and unexplored in the automotive cybersecurity space. These type of threats are targeting vulnerabilities in the Bluetooth standard. And what do I mean by Bluetooth standard? So the Bluetooth standard is a set of documents that is specifying the security mechanisms that are used by all Bluetooth devices, including car IVIs and smartphones. And if any of these mechanisms is vulnerable, then this vulnerability can be exploited on the whole Bluetooth ecosystem. For example, in 2020, we disclosed the critical vulnerabilities in the authentication protocols used by Bluetooth that are resulting in device spoofing attacks, also known as bias attacks, and this is an example of a protocol level Bluetooth threat. Furthermore, in 2019, we disclosed another PLBT affecting the key negotiation protocols in the Bluetooth standard, and we isolated that these protocols are weak and can be exploited to brute force the encryption key that is used to secure a Bluetooth connection. And this PLBT is known as KNOB, or key negotiation of Bluetooth attacks. And the important things about PLBT is that they are unexplored but very relevant for automotive. And why they are relevant? Well, because these threats are extremely portable. Once you can exploit one of these threats on one IVI, then you can port the same attack to different IVIs from different car manufacturers, IVI manufacturers, or even system-on-chip manufacturers with just minimal adjustments. And this is in contrast with implementation level bugs, where you first have to find a bug in the firmware of an IVI, and then you can write an exploit for that. But then if you want to target a different IVI from a different car manufacturer that is running a different firmware, then you have to start from scratch. Instead, with PLBT, you can port your attacks to any IVI in the market. Another interesting aspect about PLBT is the fact that they are portable across Bluetooth profiles. So here we will see attacks targeting IVIs, and we can, with the same attack, we can target all the profiles or the application layer services supported by an IVI. But if we find an attack, we can also use it on different subsystems of the car using Bluetooth, such as, for example, keyless entry systems or any other proprietary mechanism that might be based on Bluetooth. So in the next slide, we will see how we evaluated PLBTs on actual cars. In our work, we adopted an hybrid methodology, and first we started with a set of lab experiments where we first bought popular IVI second-hand from eBay, then we tried to power them up in the lab, and then we evaluated them in the lab against protocol-level Bluetooth threats such as KNOB+BIAS. Then, in the second phase of our experiments, we took our cars and we drove them in a safe environment, and then we evaluated them against protocol-level Bluetooth threats. In the lab experiment sessions, we performed the following 4 actions. So here I'm summarizing 5 months of work in just one slide. We spent 3,000 euros on eBay and bought 5 second-hand IVI used by car makers such as Kia, Toyota, Mazda, Nissan, and Subaru. Then we tried to power them up, and this is not easy as it seems, as we will see afterwards. And we had to discard the Mazda and Nissan IVIs because they were not powering up. Then we checked the Bluetooth connectivity of the IVI, and we had to discard the Subaru one. This is because an IVI might not contain a Bluetooth subsystem, but Bluetooth might be implemented by another ECU or electronic control unit, such as a telematic unit. Or another reason is that since we are buying second-hand, we cannot really know in advance if the IVI contains all of its subsystems. And so in the lab, we were left with 2 IVIs, one from Kia and one from Toyota, and then we thoroughly evaluated both of them. These are the pictures of the IVI. So as expected, each IVI has a screen and then some buttons. On the left, we have the Kia one with the model number. On the right, we have the Toyota one with the model number. So about the power up. Power up is not easy as it seems, because IVI, there is no standardized power port for IVIs. And even if you are capable of finding the power port, also the pin layout and pin count is not standardized. So as we can see from the figure on the left, the power port of the Kia IVI has 24 pins and requires 5 wires to power up. Instead, the Toyota IVI has a total of 16 pins and requires 3 pins to power up. And remember that sometimes an IVI might require additional signals to power up that might be proprietary. So there might be a proprietary CAN signal that is expected to reach the IVI that should be provided together with the power signals. And then only if you provide this proprietary signal, the IVI powers up. It was not the case for us, but that might be the case. So once we powered up the IVIs, then we performed some static and dynamic reconnaissance experiments. And now I'm summarizing the most important findings. So as we can see from the left, the car manufacturer does not always match the IVI manufacturer, because the Kia IVI was advertised as being compatible with Kia Soul cars from 2014 and 2015, but the manufacturer is Hyundai. Another interesting finding is that the production year of the IVI is typically much lower than the production year of the car. As you can see from the right, the Toyota IVI is compatible with Toyota cars from 2017, 18, and 19, but the manufacturing year of the IVI is 2012. Then also interesting to note is that an IVI can support multiple wireless technologies. So the Kia IVI supports Bluetooth and Wi-Fi, instead the Toyota IVI supports only Bluetooth. Regarding Bluetooth, interesting findings. So one is about the Bluetooth version. So Bluetooth is a version technology. The latest version I think is 5.2, and it might be from 2020 or something like that. And these IVIs are shipping with Bluetooth version 3.0. This is already a bad sign for security, because this version is from 2009, and this means that the security mechanism provided by these IVI, we already know that are outdated, and we can also deduce that the firmware that is implementing the Bluetooth stack might not be updated, might be very old and unpatched. Another interesting finding about Bluetooth is that on the hardware side, we might have some manufacturer, for example, the Toyota IVI Bluetooth system on chip is produced by Qualcomm and Alpine, and we were not capable of finding the chip producer for the Kia IVI, but the firmware, the software, might be the same even across different IVIs. So here the Toyota and the Kia are using the same Bluetooth firmware from Cambridge Silicon Radio, CSR, but in this case with different version numbers. And overall, a challenge that I want to emphasize is that it's very difficult, given an IVI, to map its prevalence in the market, because there are no public databases telling you, given the model number of an IVI, which cars are using that IVI, and what are the hardware and software specifications of that IVI. And so this means that our evaluation results, our attacks that we will see afterwards, represent only a lower bound of the impact of the attacks, because we don't really know how many cars are using the IVIs that we are testing. Now, some information about the second experimental phase, the one that we performed on the road. So we tested the 3 cars that we own. My own Suzuki Ignis from 2021, so a rather new car. Then a Skoda Fabia from 2020, owned by Matthias Peyer, that is the co-author of this security study that we are presenting in this webinar. And then a Skoda Octavia from 2021. This is owned by Aurélien Francillon, who is a colleague of mine, and he was really nice with us because he allowed us to test his car, and he is also an automotive security expert. So while we testing the cars, we didn't have, of course, the power-up problem, and it was quite easy to extract the Bluetooth specification of the IVIs running on the cars. And here we have the same problems that we've seen before, extremely old Bluetooth versions, 3.0 for the Suzuki. So even though the car is from 2021, the Bluetooth version is from 2009. The Skoda Fabia is running a slightly more updated version, 4.1, and the Skoda Octavia still 3.0. And another interesting finding is that 2 different cars from different car makers might run the exact same firmware, while 2 cars from the same car manufacturer can run a completely different firmware. As we can see from this table, the Suzuki Ignis and the Skoda Octavia are running the same CSR 8241 Bluetooth firmware, while the Skoda Fabia is running a different firmware than the Skoda Octavia, and this is from Toshiba with version number 3328. So now we're going to see how we evaluated protocol-level Bluetooth threats on the 2 IVI in the lab and the 3 cars on the road. This is our attack scenario. So we took a smartphone that is indicated as the peripheral in this figure, a modern Pixel 2 smartphone, and then we paired the smartphone with the IVI. As a result of pairing, this is a protocol specified in the Bluetooth standard that you always have to use if you want to securely connect to Bluetooth devices. As a result of this protocol, the devices are generating a long-term pairing key that in this figure is indicated with the blue key. And then we also had to accept all the permissions related to the access to contact lists and so on and so forth. And we synced the data from the victim smartphone to the target IVI or to the target car. Then, in a legitimate use case, the smartphone and the car, once they are paired, they can establish multiple secure connections. And every time the smartphone approaches the car or the IVI, the 2 devices are running a secure session establishment protocol, where first they are authenticating the fact that they possess the same pairing key, then they are negotiating a session key that is the key in light blue in the figure, and then they encrypt the traffic using this session key. And this session key protects all the services that are used by the IVI and the smartphone. And a very important difference between pairing and session establishment, that are the 2 most important security protocols specified in the Bluetooth standard, is that pairing might require user interaction. And that is why when you pair your smartphone with your car IVI, typically you have to confirm a numeric code on both screens, on the screens of the IVI, on the screen of the smartphone. And this confirmation protects against a man-in-the-middle attack. Instead, the session establishment protocol does not require user interaction. And that is why once you paired your smartphone with your car IVI, then every time you approach your car and you switch on the car, the smartphone is automatically connecting to the IVI and also is automatically syncing with the IVI. And in our attack scenario, we are assuming an attacker who wants to impersonate a trusted smartphone, so the smartphone, the Pixel 2 that we previously paired with the target IVI, to a victim IVI. And how does the attacker impersonate the smartphone? It is using a chain of critical protocol level Bluetooth threats, KNOB+BIAS. And in particular, this attack chain works as follows. The attacker has an attack device that is configured to impersonate the trusted smartphone, and then the attack device approaches the target IVI, starts a session establishment with the IVI, and then it is capable of skipping the authentication phase of the pairing key by using the bias attack, and also it is capable of negotiating a very weak session key and then brute force the session key using the KNOB attack. And by doing so, the attacker can establish a secure session with the target IVI without knowing the pairing key and the session key. And then once we are capable of impersonating the trusted smartphone to the IVI, then we can also perform the opposite and test a man-in-the-middle attack setup, where on one side we impersonate a trusted smartphone to the IVI, on the other side we impersonated a trusted IVI to the victim smartphone, and then we can man-in-the-middle or machine-in-the-middle their connection without knowing the pairing key and the session key of the victims. And why is this attack chain important and relevant? Well, because it is a very high impact attack chain. We can repurpose this bias plus knob exploits on all IVIs supporting Bluetooth in the automotive market. I don't have time to enter into the technical details about why this is the case, but this attack chain works against the strongest Bluetooth security mode. So even if an IVI would support a very high Bluetooth version with the top security mechanisms provided by the Bluetooth standard, we would still be able to exploit that IVI. And then it is high impact because it enables full device impersonation. And once you impersonate the device, then you can perform all the actions that that device is authorized to perform, including reading sensitive data from the IVI, such as SMS, contacts, notifications, and sensitive files. And you can also send malicious commands to the IVI because we are authorized to do so. So, and then we can delete sensitive data from the car. We can change the settings of the IVI, and so on and so forth. A second key reason is that they are easy to launch and hard to detect. So this is the attack chain, the most effective attack chain to impersonate a Bluetooth device. It requires no user interaction because we are targeting the session establishment protocol of Bluetooth, and also it does not trigger an extra pairing session that might trigger user interaction. And so if we require user interaction, then the impact of the attack is way lower. Other two key reasons why we are interested in to test this attack chain is that when we developed this attack chain, we did not test cars, and so we wanted to extend our evaluation to other relevant classes of devices, including vehicles, cars, but we could also have tested them on trucks or motorcycles. But we only had access to several car IVIs in the lab and three cars. But we will be happy to test this attack chain on more and more vehicles. And a fourth reason is that once we disclosed these protocol level Bluetooth threats, the KNOB one was disclosed in 2019, and the bias threats were disclosed in 2020. The Bluetooth standard was amended, and so the security mechanisms of the standard were updated to address these attacks. And some vendors from the IT space quickly patched their products against these attacks. Vendors such as Google, Apple, Microsoft, Samsung, and so on and so forth. And so we wanted to check if those patches were also applied in the automotive space, especially for this test is relevant only for very recent cars. So we were expecting a car from 2021 or a car from 2020 being patched against KNOB and BIAS, since the attacks were disclosed beforehand. So let's see the evaluation results. So the first important figure is that 5 out of 5 tested IVIs are vulnerable to BIAS plus KNOB. As we can see from this table, we have the first 2 columns surrounded by a pink rectangle are the IVIs that we tested in the lab. The last 3 columns surrounded by a violet rectangle are the cars that we tested on the road. And if we zoom in and we look at the red rectangle, we see that all devices are vulnerable to KNOB+BIAS. And more technically, regarding the KNOB attack, all devices are vulnerable to the full entropy downgrade. What do I mean by a full entropy downgrade? When we are performing the BIAS attack, we are negotiating the entropy of the encryption key used to protect the session. And typically this entropy value is equal to the key length. Key length is 16 byte, and the entropy should be 16 byte. But the Bluetooth standard includes an entropy negotiation mechanism that we can use to downgrade, to reduce this entropy. And we can reduce this entropy up to 1 byte. This means that the session key that is protecting the connection between these devices and the trusted smartphone can be brute forced just by guessing one value out of 256 values. So this is an extremely weak session key. And this is an interesting finding because when we disclosed the BIAS attack, the minimum entropy value in the Bluetooth standard was raised from 1 byte, that is the value that we are confirming in our results, to 7 byte. And so we were expecting to see 7 byte of minimum entropy in this evaluation table. Instead, we see 1 byte, and this means that none of the devices is patched against the KNOB attack. With the role switch authentication bypass trick, we also tested patches against the BIAS attacks, and since we are capable of performing this trick on all devices, this means that none of the devices is patched against the BIAS attacks. During our evaluation, we did not only test KNOB+BIAS, but we also tested a different protocol-level Bluetooth threat called just work downgrade attack. This is an attack that targets the pairing protocol and not the session establishment one, and it enables to pair with the target IVI while impersonating a trusted device without requiring user interaction. And out of the 5 devices that we tested, only the Suzuki Ignis was not vulnerable to this just works downgrade attack. During the evaluation, we also tested the pairing and session establishment capabilities of the devices, and we can tell that the pairing ones are okay because all tested devices are using secure simple pairing. That is the most secure pairing protocol provided by the Bluetooth standard. This protocol is based on asymmetric crypto primitives, and in particular on elliptic curve Diffie-Hellman, and by itself protects against eavesdropping attacks. Then all the devices are declaring input-output capabilities, and attacker in the middle or man in the middle authentication requirements, except for the Toyota IVI. And eventually, given these capability sets, all devices are negotiating an authenticated version of SSP, of Secure Simple Pairing, that requires numeric comparison. And so as a bottom line, this means that during pairing, if you use the default pairing configuration, the user is protected against man-in-the-middle attacks. Instead, the session establishment capabilities of the devices are very weak. None of the devices support a security mode called secure connections, and by not supporting this mode, this means that all devices are defaulting to unilateral authentication of the pairing key during session establishment. So if you remember when we described the KNOB+BIAS attack chain, we said that during session establishment there is a first phase where the devices should authenticate the pairing key. But since secure connections is not supported, this authentication is already weak by itself because it is performed only by one device and it is not mutual. Plus, the session is encrypted with the session key using the E0 cipher. And this E0 cipher is weak because it is not a standard cipher like AES in CCM mode, and also it does not provide message integrity but only confidentiality. Now, how can you reproduce these attacks in your lab? So this is our attack device that consists of a Linux device. We are using a common Linux laptop attached via USB to a Cypress development board. The exact model is CYW920819. And if we look at the logical components of our attack device, on the left, so the Linux laptop is implementing the Bluetooth host. The Bluetooth host is a part of the Bluetooth stack that manages the high layer protocols such as the transport and application layer ones. And the host in a Linux-based system is implemented by two key components. One runs in the Linux kernel, and then one runs in user space. The user space component is also known as BlueZ. And then instead, the development board implements the Bluetooth controller, that is the component of the stack that is managing the physical layer and the link layer, so the lower layers of the stack. But it is also implementing the security mechanisms that we are attacking, so the pairing and the secure session establishment mechanisms. And the host and the controller are communicating via a well-known interface that is known as HCI, or host controller interface. So the setup of our attack device requires a bit of technical expertise for two main reasons. The first reason is that to monitor the packets sent at the link layer, so the sent over the air by the controller, we need a modified Linux kernel that we developed that is capable of parsing these special packets. And how can we get these special packets? We can send a proprietary command to the development board and tell the development board to copy all the link layer packets that are sent and received, and then send those packets over HCI. And so this is the first technical mod that must be performed in order to monitor both the HCI traffic that is going on between the Linux laptop and the development board, so between the host and the controller, but also to monitor the link layer traffic from which we can see what the remote device is telling us. And the second technical aspect is related to the Bluetooth firmware of the development board. So unfortunately, at the moment, there are no open source Bluetooth controllers available, and so we need a workaround in order to modify a Bluetooth controller. Why do we want to modify a Bluetooth controller? Because the security mechanisms of Bluetooth are implemented in the controller. And for example, if you want to downgrade the entropy of the session key, then we need to modify the controller. We cannot do it from the host. And currently, the workaround that we are using relies on Internal Blue, that is an open source framework for reverse engineering and security evaluation of Bluetooth chips. This framework is really nice, and it supports several devices, including this development board. and it provides a high-level Python API that is capable of reading and writing data at runtime, so we can see what is going on in the firmware memory at runtime and change some of these parameters. But we can also write our patches in ARM, because the development board run on the Bluetooth firmware runs on an ARM Core M, and so we can write patches in ARM and then send these patches dynamically to the Bluetooth firmware and execute also custom code at runtime. And so, for example, if we want to, with our attack device, if we want to test the KNOB attack, what we can do, we can write a Python script that is using this high-level Python API provided by Internal Blue, and the Python script looks as follows. So we need first to isolate the addresses of the entropy values stored by the Bluetooth controller in the Bluetooth firmware. And in this case, we reverse engineer these addresses from the firmware. Remember that the firmware is closed source. We cannot recompile the firmware. We cannot inspect its source code. We have to reverse engineer all the information. So we reverse engineer the address of lmin and lmax. Lmin stores the minimum entropy value supported by the development board. Lmax stores the maximum one. And by using internal blue.writeMem, we can pass two parameters, the address in RAM that we want to write, and also the value that we want to pass. And in this case, we are writing 1 because we want to test the KNOB attack. And with this very simple patch, we can simulate kind of a man-in-the-middle attack, because we are patching our own controller from one side, and so we are using our own attack device both as the victim, one of the victims of a man-in-the-middle attack, and also as the attacker. And then we can test any other remote device against a KNOB attack. If the remote device accepts 1 byte of entropy, this means that the remote device is vulnerable to KNOB. And this is what you can do to test, for example, a KNOB attack against an IVI. You reproduce the attack device, you just write this value in memory, and then you test you start a secure session establishment, you monitor the link layer packets, and then if you see that the IVI is accepting 1 byte of entropy, this means that the IVI is vulnerable to the full KNOB downgrade. Then you can, of course, change the minimum and maximum values. For example, you can test 7 bytes of entropy, you can test 8, 9, 10, up to 16. You can even test values out of the specifications. If we want to reproduce instead the bias attacks, the technical setup is a bit more involved, because now we need to also impersonate the device. And to do that, I developed a custom software module that has written in Python, that is on GitHub. And actually, this module can also be used to test the KNOB attack. So if you have the bias setup working, then you can test both KNOB and bias at the same time. And how does this bias module work? Well, it expects two files, an impersonation file, or IF, and an attacker file, AF in short. And then it spits out a bias.py script that is compatible with internal Blue, that can be used to write data to the Bluetooth firmware at runtime to impersonate a device, but also to patch the code of the firmware at runtime. So, for example, let's look at an impersonation file. An impersonation file is just a simple JSON file containing information about the device that you want to impersonate. For example, this is an excerpt from the impersonation file for a 7th generation X1 ThinkPad Carbon laptop that I impersonated, and you have several fields, and each in the lmin and lmax field you can set the entropy value that you want to set for that impersonated device. Then you have to reproduce the Bluetooth name and the Bluetooth address of the impersonated device. And if you look at the GitHub repo, you can see the full IF file. And this is useful because by using this system, if we want to impersonate a new device, we can simply take an AF file as a template, we can copy paste it and then change only the fields that need to be changed. The attack file instead is useful because I wanted to create a toolkit that does not depend on the development board that you are using to patch the Bluetooth firmware and to attack. This means that if Internal Blue supports multiple development boards and we have ways to patch those development boards at runtime, and we reverse engineer the address of the functions that we want to patch, the addresses of the data that we want to patch, then we can use this this attack file to match a different board. Now I'm only in the repo. I'm only providing one attack file for the development board that we've seen so far. And in the attack file, this is still a JSON file. You can specify the architecture. So our development board is ARM32, little endian using thumb only mode. You can specify the HCI interface that the board is using to communicate with the laptop. And then you need to specify some aspects of the firmware that you have to reverse engineer by yourself if you want to extend the toolkit to use, for example, another board. And then the BIAS repo includes this bias template.py that is a Python script that is parameterized by the IF and AF files that you are passing to the toolkit. And this template file contains, among others, some patches. Here I just wanted to show you how you can develop your own patches if you want to test something else. For example, this patch stored in a string named code1 is a patch to always switch to the central role. So you have to create like a binary string, and then in the binary string you have to write ARM assembly code. And then you perform some code manipulation, and then eventually you can use this internal blue.patchrom API. You need to pass the address of the patch and the content of the patch. So if you want more information about the BIAS repository, you can check it out on GitHub, and then you can clone it. And you can look at the README, and you should be able to reproduce the attack setup that I've just described. Now, to conclude the talk, I want to show more resources and to do some acknowledgements. So the paper about the PLBT evaluation, and also the evaluation study that we talked so far, is titled "On the Insecurity of Vehicles Against Protocol-Level Bluetooth Threats." And this is the same title as the seminar, and this paper was presented at WOOT, that is the Workshop on Offensive Technologies. This is a premier workshop for offensive cybersecurity research, and you can download the paper if you want to get more information about the study. I'm also linking the paper about the KNOB attacks. This paper is titled "The KNOB is Broken, Exploiting Low Entropy in the Encryption Key Negotiation of Bluetooth-BR EDR." So there are two papers about the KNOB attacks. This one is about Bluetooth-BR EDR, that is the flavor of Bluetooth that is used by the IVIs. And this is also known as Bluetooth Classic. Then there is also Bluetooth Low Energy, that is a different flavor of Bluetooth, more suited for very low power wireless services. And actually Bluetooth Low Energy will also be used by Automotive, or maybe it is already been used for some proprietary services. And the interesting thing is that the KNOB attack works both on Bluetooth Classic and Bluetooth Low Energy. And this one instead was presented at the Unix Security Symposium in 2019. Then the BIAS attacks. This is a family of attacks against Bluetooth BR EDR or Bluetooth Classic, family of impersonation attacks. I'm leaving the link to the paper in this slide, and this paper was presented at the IEEE Security and Privacy Symposium in 2020. I also would like to acknowledge several people that helped me quite a lot. The first one is Andrea Amico, the CEO of Privacy for Cars. Andrea actually reached out and suggested me to test this KNOB+BIAS attack chain on automotive devices, and he also provided funding to buy the IVIs that we bought second-hand from eBay, and also provided industrial expertise. I would also like to thank Jean-Michel Crepel that helped me quite a lot with the experimental part. He set up the lab bench, and he reverse engineered the pin layout of the IVIs, and so his help was instrumental to perform our evaluations. I also would like to thank Aurélien Francillon because he allowed us to test his car. Aurélien is a colleague of mine at Eurecom, and he is also doing research in embedded systems and automotive system security. Finally, I would like to acknowledge Niels Ole Tippenauer, professor at CISPA, and Kasper Rasmussen, a professor at the University of Oxford, who are the co-author of the KNOB and BIAS research papers. And this slide concludes the webinar and kind of wrap up the key takeaways from the webinar. So during the webinar, we've seen a study on protocol level Bluetooth threats, and we've seen that this is an unexplored but very relevant attack surface for automotive cybersecurity, especially because these threats, unlike implementation level Bluetooth threats, are extremely portable. So you can repurpose the same protocol level attack on all automotive devices like IVI units, for example, that are currently in the market. Then we've seen a low-cost methodology to assess these threats based on some experiments in the lab and on the road. Then we've seen how we evaluated 5 recent and popular IVIs against protocol-level Bluetooth threats, and we've seen several interesting findings. For example, we've seen that it is trivial to spoof a trusted smartphone to an IVI. Then we can also mount then a man-in-the-middle attack between the IVI and the trusted smartphone. That the IVIs that we tested are using a very weak session establishment capabilities, and so on and so forth. Then we also talked about our setup to reproduce the attack that is quite low cost, and the code is open source on GitHub. There is some technical effort required to patch the Linux kernel and also to understand a bit the dynamic patching of the Bluetooth firmware of the development board. But once past that technical part that I think is also fun, then you can even repurpose this setup to test other protocol level Bluetooth threats. And then if there are any questions, you can reach me out via email or social media. Please visit my website if you want to find contact information about myself, and thank you for listening.